So this is part B, the follow-up of lecture 2 of week 7 of the class Neuronal Dynamics. We work with the ADEX model. We just have two equations. Spikes are generated at the moment when the voltage, which is controlled by the first equation, hits a threshold. At the moment of a spike, or more precisely, immediately after the spike, the second variable jumps by an amount, b, that's this parameter here, while the voltage variable is reset to a reset value UR. Now there's a further important parameter, and that's this parameter A. It corresponds to the slope of the W null line. If you do a null line analysis, you can forget about spikes. You solve the null line equation by setting the left-hand side to 0, and the result is W equals A times U minus U rest. And that means the W null line is a linear function of the voltage. So let's look at the null lines. And to do this, we start with a simple case. We set this parameter A, the coupling between the voltage and W, to 0. Recall that for adaptation, the standard input is a step current. So before the step, the input is 0, and after the step, it has some positive value. The W null line is a straight line with slope A equals 0, which means it's a horizontal line. Now, the U null line for I equals 0 is just this curve here with a linear and exponential part. That's the shape that we know from the exponential integrated fire model. Before the current is switched on, there's only one fixed point, one stable fixed point here. That's the resting value. But now we switch on the current. If you switch on the current, we now have a constant value I1, and the result of this is that the U null line is shifted vertically upwards. The fixed point therefore disappears, and the voltage will move. It will follow the W null line until it hits the reset threshold about here. But then we know at the moment of reset, the W variable jumps by an amount B, while the voltage is reset to UR. So let's take UR equal minus 60 millivolt. The jump, the reset, ends at this point. And from there on we have to follow the arrows. Arrows are vertically on the U null line and slightly diagonal downward to the left in this region up here. That means if we project down to the voltage equation, the voltage initially decreases before it increases again. And that's what you see here. Initially the voltage decreases after the reset, and then it increases again. Thus, this choice of parameter gives fairly regular tonic firing with characteristically a dip in the voltage trajectory after the reset. So that's one choice of parameters, a fairly large jump size B. Let's now look at a different choice of B. Again, A is set to 0, so that the W null line is a horizontal line. Once the current is switched on, the voltage moves towards the upper threshold, And now W jumps by an amount B, while U is reset to UR, so the new starting point is here. And the same thing happens again. B jumps again, second trajectory. W jumps again by amount B, and again, and again. So the result is that we have repetitive firing. However, if the trajectory starts up here, the size of the arrows is actually smaller than down here. That means initially the movement is a little bit slower, and that's why interspike intervals after reset number 6 and reset number 7 are longer than at the beginning. Also note that there's no dip in the voltage trajectory. Once we have reset, the voltage moves immediately again upwards. So, this choice of parameter will lead to adaptation. Let's have another example. Let's now consider the more general case that this coupling parameter is positive. So the U-0 line now has a positive slope, characterized by this parameter A. Before switching on the current, the neuron was sitting at its resting potential, a stable fixed point, but after the switch, this fixed point has become unstable. So the voltage will move upwards, a spike is initiated, and then we have a reset from this value to a new value. The voltage is now reset to say minus 50 millivolt, and B is in the medium range. So after the first spike, the trajectory starts here, then it's reset again, it will start here, it's reset again, it starts here, and it's reset again by an amount B, starting from this point here. So the result is that we have initially a rapid sequence of spikes. It's only after spike number 4 that we see this dip in the voltage. And that's related to the fact that the trajectory starts above the green curve, where the arrows are pointing slightly leftward. So let's look at this trajectory. Well, I would classify this as initial burst followed by tonic firing. So we have discussed 3 examples. All 3 examples use the same neuron model. A neuron model is containing 2 equations, a voltage equation and a second equation for the adaptation variable with reset conditions. U is reset to UR, W jumps by an amount B. And this same neuron model can account for different firing patterns just by choosing the parameters A, B, and UR in the appropriate range. And we can predict the appropriate range by the phase plane analysis methods that we have discussed together. Thus, let's take a nonlinear integrated fire model, and the best choice is linear plus exponential. Let's combine this with adaptation variables on a slower time scale. Then we can account for diversity of firing patterns. However, so far this parameter theta was still fixed. But we can make this parameter dynamic. This is my theta, and it has a standard value, theta 0. And then after each spike, it's increased by some amount. And you see the shape of theta 1 in this little curve here. It goes up and it goes down again. This is the value theta 0. The difference between those two is theta 1. Now if there are several spikes in with short intervals, then it can actually increase to higher and higher values. And this causes a different form of adaptation. Let's summarize. We can start with the exponential integrated fire model and add one or several adaptation variables. And suddenly, we are able to account for a whole variety of different firing patterns in response to step current input. So, our neural model is now very flexible, but it's still a deterministic model. We should also account for noisiness, for variability in spike trains. And that's what's going to come in the next few lectures.